Yeah, so we derived this dispersive pulse propagation, and which we can use to see how basically pulses broaden by going through a fiber, right? And we also discussed this phenomenon of chirping, which is basically the instantaneous frequency within the pulse being time dependent, right? And that is also something that arises out of dispersion, right? And it can also, I mean, a most general optical pulse is can be described as a chirped pulse, right? And so sometimes, like out of optical transmitters that I use, like semiconductor lasers, for example, where the pulse is coming out, when we modulate the current, the pulses coming out could already be chirped. Okay. So anyway, so we'll discuss that briefly. So we'll look at how these pulses get transformed while traveling through an optical fiber, right? And mathematically, how we can sort of use that to calculate the amount of broadening happening and use it to design our links. Right, so recall basically, so we started typically, let's say, right at the transmitter end or something, we will start out with some pulse here, and then we send it through some optical fiber of length L. So this could have, let's say, a GVD coefficient beta 2, right? Or equivalently, the dispersion parameter D, right? We could also include higher order dispersion terms we discussed, right? So right at the output or the receiver end, this pulse gets transformed, right? Either broadened or the equivalently the chirping is changing, right? So using this pulse propagation equation, we call that was something like this, right? So if we include up to third order dispersion, right? It looks like that. We could include higher order dispersion also, beta 4, then that could have a D4A by DT4 term, right? And so on. But typically, at least for telecom applications, up to third order is more than enough, right? And we said basically how to solve this equation is, so if we start with something here, right? So at A0 comma T, that's some pulse. So that defines my envelope here, right? And of course, it's multiplied by some carrier frequency. And there could be some chirping, again, defined by the C parameter that we had taken, right? So what we do is we first calculate the spectrum here, right? And then basically this fiber, what it's doing, we saw the dispersion can just be treated as a phase shift in the frequency domain, right? So basically, this fiber propagation, you can just take, so A after the fiber propagation is just the input spectrum multiplied by this phase factor, right, which depends on the propagation length, and then so beta 2 times omega square, so quadratic frequency dependence of the phase shift due to GVD term, and then again you want to include higher order terms, then we have beta m times omega to the m. right? So then we now know the spectrum here at the receiver, and then to calculate what is the pulse looking like here at the receiver in time domain, we just take the inverse Fourier transform here to go from frequency domain back to time domain. Right? So let's say here if we start with a general chirp Gaussian pulse at the transmitter end, so again that would be something like this. Right? So T naught is sort of roughly like the half width of the pulse, right? And C is this chirp parameter, right? Which we discussed last time. So if C is positive, frequency is increasing with time in the pulse. If C is negative, frequency is decreasing with time. If C is zero, it's a transform limited pulse with a constant carrier frequency. Right. So let's say we have this sort of general pulse at the input. Right. So then we can follow this procedure. Right. And if you have a Gaussian envelope like this, then it's also very easy to take Fourier transforms and inverse Fourier transforms. So we call this formula that we had for Gaussian integrals last time with complex coefficients. Right, we can easily use that to calculate the spectrum here, and also once we multiply with the phase here to calculate the spectrum back. See, so in the first, in most cases, so if you're operating away from the zero dispersion point, right? So if beta 2 is finite, right? So if you're not at the zero dispersion wavelength, then typically beta 2 dominates over beta 3. Okay. So in that case, basically we can neglect this third order term. Okay. Okay, and then we can basically so if you don't have this third order term here, you can see that this phase shift is also like a Gaussian term, right? It's like omega square in the exponent. So again, we can use the simple integral formulas and basically calculate all this analytically, right? For beta 3 equal to 0, we can easily do that, and you can see that. Sorry.
The bracket term beta to finite में क्या है?
Yeah, this away from the zero dispersion wavelength, away from ZDW.
Okay, sir.
So again, recall that as a function of wavelength, if I plot beta 2, so D went from negative to positive, beta 2 will go opposite positive to negative, right? So there will be some zero dispersion wavelength here, right? At which this is 0. I'm saying if you operate away from this, right? So typically we saw that for single mode step index optical fibers, this was around 1.3 micron. So if you operate close to that, then this term will be small, right? Because beta 2 is close to 0. Then you have to include this higher order term. But if you're operating away from that, typically the beta 2 term is dominant over this, right? So I'm saying we are operating here, and we can neglect the beta 3 term in that case. Okay, and in that case, basically all the this can be analytically solved, and all the functions here remain Gaussian, right? Because you have Gaussian function in the time domain, you take the Fourier transform, you get a Gaussian function in the frequency domain. Now you multiply by this phase. For the beta 2, it's still a Gaussian, right? When you take the inverse Fourier transform, you again get a Gaussian pulse. Okay, so in this case, everything remains Gaussian, of course, with complex coefficients. Okay, so if you follow this procedure, basically you can get the output pulse. Okay, so this is some A naught amplitude here given by the power in the pulse. So the output pulse looks like this. You can try to do this at home yourself to derive this expression based on the integral formula that we discussed last time. So basically all you need is this formula. You apply it at every stage. Okay, where A and B can be complex numbers. So in this case, of course. Okay, so you apply this formula to take this Fourier transform. Of course, this is just a multiplication, and then here also when you take the inverse Fourier transform, you can use the same form. Okay, so you end up with something like this. Okay, so you can see that the form is exactly the same as the input pulse, except you have this factor Q, which depends on the length here, right? So the peak amplitude has decreased, okay, and this QL is also now multiplying with T naught. So the pulse width in general has increased, right? So depending on the magnitude of this Q, right, the peak amplitude has gone down and the pulse width has increased. So that has to happen because again there is no loss, right? So the total energy in the pulse is conserved. So basically, once you broaden, right? So if the input pulse was something like this, the peak amplitude goes down and the width increases. Right, that is for the case when Q would be greater than 1. Right, but we'll see that you could also have the other case depending on this C and the sign of this beta. Anyway, so you get this, and what is QL here? Okay, it's some quantity which depends on the GVD coefficient of the fiber beta 2 times the length and also the initial chirp C on the pulse. Okay, so you can try to rewrite this again. So again, Q is, again you can see here a complex number, right? So you can try to rewrite this again in terms of this kind of form. So you separate this into real and imaginary parts, right? Take Q as this and then try to separate this into real and imaginary parts. So the real part will give me the effective pulse width, right? So if I write this as e to the minus t square by 2 TL square and then 1 plus ICL, right? So separate this into real and imaginary parts, right? So then I will get, if I write it like this, then you can comparing with this, T sub L gives me the pulse width now at the receiver, right? And CL gives me the chirp at the receiver, right? So basically you can see what has happened due to this dispersive propagation, right? If we have only GVD, then basically the pulse width and the chirp of the pulse have changed depending on the length and this GVD coefficient. Okay, and so by comparing this, I can find out what TL is in terms of T naught and Q, which also again depends on beta 2, right? So if you do that, so firstly, if you can get both TL and CL in terms of the input parameters and the fiber parameters, right? So the chirp at the output is basically the chirp at the input. So maybe I should call this C naught here. B naught, this is the input chirp. C naught. Right, so CL will be C naught. Okay, so that's the chirp at the output after propagating the fiber of length L. Right, the output chirp looks like that. Right, so it depends on the, of course, the fiber parameters, the GBT coefficient, and the length, but it also depends on the input parameters, the input chirp and the input pulse width. Okay, so similarly, if you look at the pulse width, okay, so that looks like this. Okay, so again you can see now it depends on this beta 2 times L, also on the input pulse, right? So now this is recall slightly different from when we considered the case of an incoherent, right? So here it's a coherent transmitter or like a single frequency laser, basically, right? So the carrier frequency is omega naught, a single frequency. When we considered an incoherent source with some finite bandwidth, right? Then basically we just saw that the broadening in the pulse just depends on this beta 2 times L times the bandwidth of the source, delta omega, right? So that is independent of like the pulses here, right, or the data rate you're using here. But in this case, right, for coherent sources, you can see that basically the output pulse width depends on the input pulse width also, in addition to the fiber parameter. Okay. So this is going back to the fact that we discussed that. So from that initial formula of the broadening being proportional to the source bandwidth, if we just keep reducing the source bandwidth to 0, does that mean the broadening just goes down to 0? It doesn't, right? From here, basically, once your line width goes below sort of the data rate or 1 over T naught, then now T naught itself starts limiting you. Okay, so yeah, so one thing to see here is that okay, sometimes so this is written in a slightly different form. So there is this quantity called the dispersion length, okay, which is defined as the square of the input pulse width divided by the magnitude of the GBT coefficient of the fiber, right? So to take the mod, it could be positive or negative, right? So this has units of length because why? So T naught square has units of time square or second square, right? Beta 2 recall had units of like picosecond square per kilometer, right? So this is picosecond square, this is picosecond square per kilometer. So you can see this will give you kilometer, right? So this is called dispersion length. Right, because you can see this quantity shows up here, beta 2 by T naught square, beta 2 by T naught square, right? Beta 2 by T naught square. So I can also write, so the fraction by which the pulse has broadened, right? So the output pulse width divided by the input pulse width. So this is the broadening factor. Depends on the dispersion length, right? So this I can write as right? So you can see the broadening depends on basically how long the fiber is compared normalized to the dispersion. Right. Another way to define the dispersion length sort of is that, so if you take an unchirped input pulse, so if C naught is 0, right? So this first term is just 1, right? This term is 0. Then you can see that for L equal to LD, TL is square root of 2. So for unchirped input pulse, TL becomes square root of 2 times E naught at L equal to LD. Right? So basically it's the length after which the pulse width broadens by a factor of 2. Right? And you can see, so it depends on the input pulse width. If you have a shorter pulse at the input, you can see that the dispersion length is smaller, which means that it broadens faster. Right? And why is that? Again, recall from Fourier transform, a shorter pulse means more frequency components. Right? And more frequency components traveling through a dispersive medium means they these different frequency components are traveling at different velocities, so they would spread more, right? If you have more spreading frequency. So that's why if you have a shorter pulse at the input, it will broaden faster, right? Characterized by shorter dispersion length. Also, dispersion length is inversely proportional to the GVT parameter here. Again, that is sort of obvious. A higher GVT parameter means more dispersion in the fiber, right? Which means the pulse will broaden faster. Right? LD will be small. So that's one thing. Another thing to note is actually what happens to the chirp, right? So here you can see that, yeah.
So it will be to the power half TL by TO expression.
Yeah. This is yeah, that's why root 2, right? 1 plus 1. Yeah, so you can see that there's this term here which depends on the sign of beta 2 times the initial chirp. Right? So what is happening because of dispersion here, right? Dispersion is adding a phase which is giving a chirp, right? So again, we discussed this in the beginning. Basically, different frequency components traveling at different speed means that the pulse gets chirped, right? So either the low frequency components go ahead or the high frequency components go ahead, depending again on the sign of this beta 2, right? So the fiber, due to its dispersion, is introducing a chirp, and then you have an initial chirp on the pulse, right? So if these two are of the same sign, right, then you can see that basically the fiber will make the chirp of the pulse even worse, right? It's adding on the same sign. So the pulse will broaden more, right? So if beta 2 times, so beta 2 and C naught are of the same sign, then basically the chirp added due to the fiber adds on top of the initial chirp and you get more broadening. This factor is larger if this is positive, right? But you can see that if this is negative, so beta 2 times C naught is negative. So either C naught is positive, beta 2 is negative, or beta 2 is positive, C naught is negative. Then this will be a negative number, right? And depending on this again, values of this, you can see this will be 1 minus something, right? So this could actually be a smaller number, and if the numbers are sort of the magnitudes are correct, you can actually get where PL might actually even be smaller than T naught, right? You can also see from here. So let's say C naught is positive and beta 2 is negative, then you can see CL will be less than C naught, right? So the chirp is going down, right? Which means it's from a chirp pulse we're going towards an unchirped pulse, right? And we already saw that an unchirped pulse or the transform limited pulse has the minimum duration, right? Again, For this chirp pulse, recall that the duration T naught dependent on the chirp like this, delta omega, where this is the bandwidth. Right? So for C naught equal to 0, you get the minimum pulse width, which is 1 over the bandwidth. Right? So you can see if C naught is positive, beta 2 is negative, C is decreasing, and you're approaching a transform limited pulse. So the pulse width is also decreasing. Same case the other way, if C naught is negative, beta 2 is positive, you can see that again the magnitude of CL will be smaller, right? You're approaching 0 from the other side. Right, so basically it depends on the sign of beta 2 times C naught. And I mean, from here you can calculate at what distance CL will become 0, right? You can see starting from some initial chirp, if beta 2 is the opposite sign, at some point, at some L, CL will become 0, right? At that point, the pulse will have its minimum width, right? So it will actually compress. If C naught and beta 2 are opposite signs, the pulse will actually initially compress up to this point where CL becomes 0, and then if you propagate further, then it will start broadening again, because right after 0, then CL will again start increasing in magnitude. Right. So the point is, if beta 2 and C are of the same sign, then the pulse starts broadening from beginning itself and keeps broadening. If beta 2 and C are of the opposite sign, then it actually compresses for some length, and then depending on what the total fiber length is, if it's more than that length at which it goes down to 0 chirp, then after that it will start broadening. Right, so now you can see why this initial chirp can be important, right? If I had an initially unchirped pulse, so if C naught is 0, then the pulse will always broaden, right? No matter if beta 2 is positive or negative, the magnitude of CL will always be more than 0, right? So if we start with an unchirped pulse, then it will always broaden. But again, if you have designed the pulse such that your initial chirp is opposite to the chirp introduced by the fiber, then you can actually get pulse compression for up to some length. Right, so you can calculate from here. Right, and the data rate that I can operate this link at is of course limited by TL, right? So at the receiver I am getting pulses of duration TL, right? So you can see that my bit rate, the bit period here is limited by TL, right? If TL increases, then if I keep the bit rate the same, then I start getting this intersymbol interference, right? So you have to keep the bit period at least some factor larger than this TL, right? So TL is basically what will determine your operating data rate. Okay, so yeah, from here we can see that so C at particular L equal to L min will become 0, right? So if you just put this equal to 0, we get this L min depends on the initial chirp and this dispersion length. Right? So of course this is for the sign of beta 2 C0 less than 0. Then basically the pulse will compress and then reach a minimum width after this length. Okay, and the pulse width at this minimum length, you can again just plug in that L here, this element here. So that will be, you can already guess what this should be, right? Again, from here. Right? So the minimum T min, as we know, is 1 over delta omega, right? When this is 0. And the pulse we are starting out with has a width square root of 1 plus C naught square, right? So the minimum pulse width would be the initial pulse width divided by, right? So basically you get pulse compression up to L min. And then beyond L min, again, the pulse starts growing. So if you plot basically this variation, right? So on the y-axis, I have the pulse width or the broadening factor TL by T naught. And on the x-axis, I have length normalized to the dispersion length. Okay, so let's consider a case. So for this, let's consider the fiber to have positive beta 2, right? So this is, as you know, normal or normal dispersion. Right, and now we can look at how pulses with different initial chirp, how they propagate. So again, we can start with an unchirped pulse, so C naught equal to 0. So that goes something like this. So some numbers here. Okay, so this goes up to 2 at very little speed. So this is the unchirped pulse. Right, again, so it starts broadening from the beginning. And now we can look for a higher chirp, for a positive chirp. So we know, so here the dispersion is positive. So for a positive chirp, it should broaden even faster, right? Because this term you can see will be larger now, right? So if I look at C naught equal to 2, for example, that goes like this. Right, so it broadens faster for beta 2 C naught positive number. If I take the other case, C naught equal to -2, so now beta 2 times C naught is negative, right? And then we have this case. So it will compress initially. Okay. So it will start compressing initially up to some length here. Okay, so again, if you put this C equal to 2 here, then you get like 2 by 5, so that's 0.4 times LD. So until 0.4 times LD, it compresses, and then it starts broadening. Okay, so this is the negative. Okay, so now you can see, depending on your link length, you can see like which ones is better, right? So of course C0 equal to 2 is the worst always because that broadens the fastest. If your link length is up to this point, then you can see that C0 equal to -2 is actually better than the unchirped pulse, right? And then if you go for a longer length beyond that, then the unchirped pulse is. And you get the same curve if I switch the signs, right? So if I make now this anomalous dispersion, so recall normal dispersion happens for your conventional step index fibers below 1.3 micron, right? And above 1.3 micron, which is basically our telecom range of operation, actually there is anomalous dispersion, right? So beta 2 becomes negative. Right, so there basically these will switch. So now -2 will broaden fastest, and then +2 will first compress in them. Right, so again, it's basically this sign of the beta 2 times C0, which is determining how the pulse goes. Okay, so yeah, I hope all this discussion is clear, right? Basically, it's an interplay between your initial chirp on the pulse and the chirp introduced by the dispersion in the fiber. Okay, so this basically, again, if you go back, we started from this pulse propagation equation and neglected the beta 3 term. We said beta 2 is dominant over beta 3. But if you include the beta 3 term also, one can calculate what this broadening factor will be. Of course, it becomes much more complicated. Also, the pulse does not remain Gaussian anymore, right? Because so now if you include this factor, the pulse does not remain Gaussian, and it also doesn't remain symmetric. Okay, so it starts looking like this. So it might have some oscillations like this, and then it looks asymmetric about the peak. Include this term. Okay, but nevertheless, one can calculate what this would be. So let's just quickly, especially that will be important if you are operating near the zero dispersion wavelength, right? So then beta 2 term is very small, so then beta 3 term becomes important. So just to give you some idea of this dispersion length, right? So again, so if you take a standard single mode fiber, if you look at beta 2, that's about so let's say at the telecom wavelength 1.55 micron, it's about -20 picosecond square per kilometer, right? So if I send 20 picosecond pulses, you can see that dispersion length will be a kilometer. Okay, so that's the scale over which the pulse is broadening. So after 1 kilometer of propagation, the pulse will become square root of 2 times. Of course, you start with unchecked, right? So that gives you sort of some scale. We should know the amount of chirp, yeah, right? So C0 is basically the amount of chirp introduced by the transmitter itself, right? That's what C0 is. That's the chirp we are starting with. So there are ways to measure pulses and figure out what chirp it is, right? So you can measure the pulse here, and you will figure out what chirp it is here and at various places. So those techniques exist when you can measure the pulse and figure out what chirp it is. Okay. That's not. Yeah, so if we include the third order term also, then this formula, we get an extra term corresponding to the beta 3. Okay, so yeah, so these first two terms are the same terms here, you can see. Then we get an extra term because of this beta 3. And now we get a term something like beta 3L divided by T naught cube, right? So for beta 2, we had a T naught square. Here we get a T naught cube. Why again? So what are the units of beta 3 is the third derivative of the propagation constant with respect to frequency, right? So this will have units of picosecond cube per kilometer. So that's why this will be cube. Yeah. Okay, and then we can generalize this formula even further. Recall this entire discussion is for a coherent source, right? So single carrier frequency here, omega naught. But let's say you also include some finite line width for the source, right? So actually there is omega is not fixed, but there is some bandwidth associated with that, right? You can sort of semi-analytically or heuristically calculate a formula by including that finite bandwidth effect also. Okay, so in the most general case, so if we generalize finite bandwidth sources, we can write the most general formula for this broadening. With square here. Yeah, all these formulas are given in your textbook, etc. So don't worry about remembering each and every term, anything like that. You should just be aware of how things scale with our different parameters. But yeah, so this is the most general formula that one can use to find the dispersive broadening, right? So Vs here is a parameter which characterizes the coherence of the source. So that's the bandwidth of the source, delta omega s, multiplied by the pulse width, T naught. Okay, so this is something like the source coherence. Right, so if this number is very small, much less than 1, So if delta omega s is very small approaching 0, much smaller than 1 over T naught, then Vs is much smaller than 1. That is what we mean by a coherent source, like a single frequency laser. Right? So Vs much less than 1 implies coherent source. And if Vs is bigger than 1, then now it's an incoherent source. Right? If the source bandwidth is bigger than 1 over T naught, then it's an incoherent source. So that factor is now included here. Okay, so yeah, with this most general formula, we can compute the broadening for any type of fiber using its beta 2, beta 3 values, and also for any type of source by including the source bandwidth. Okay, so and again from this PL, right? As we discussed, that will determine our data rate, right? Yeah. So if we just maybe focus on this most general formula for now, and look at this in various limits. So if you look at the bitrate limitations that we get due to dispersive broadening. So let's first look at incoherent sources, which was sort of used up until the latest generation of the optical communication system. So maybe until the 90s, incoherent sources were used like laser diodes or LEDs. And even now for some short haul links like below a kilometer length scale, we still use incoherent sources because they are much cheaper to make and use. So yeah, so this is basically DS is much bigger than 1. Right, so for incoherent sources, basically, as we discussed, this broad bandwidth, source bandwidth, is coming because of frequency and phase fluctuations in the carrier, right? So if you look at within the pulse, how the instantaneous electric field is varying, that's sort of randomly oscillating, right? You can't identify some particular frequency or phase here, right? So basically, the effect of chirp sort of becomes unimportant, right? It's hard to even define a chirp for such a case, right? Only when you have nice oscillations can you define well-defined phase. You can define a chirp, right? How the instantaneous frequency is varying with time. So for these incoherent sources, like chirp sort of becomes meaningless, right? So the dominant term just comes with the terms with Vs. So Vs times this is the most dominant term. Okay, and if you're operating close to dispersion. If beta 2 is very small, then this next term with Vs. Okay, so let's say we are operating away from the zero dispersion point. So if beta 2 is not negligible, then you can see that basically if I neglect all the terms except so this term, right, and then for Vs I put delta omega s times T naught, right? So Vs square, I get a T naught square that will cancel out with this T naught square. So I just get this, right? And you can see, so this is sort of like the broadening, right? So we recover this formula that we had in the beginning, right? For dispersive broadening, the GVD times length times source bandwidth. Okay, equality in wavelength again, looks like this. Yeah, so yeah, just checking that in the limit of incoherent sources, we recover back the formula we had. Right, so basically at the transmitter, if I have pulses with T naught, basically at the receiver, I'm getting pulses of TL, right? And this broadening here is given by this, right? So typically, like, let's say to avoid intersymbol interference, or to keep the errors below a sufficient threshold, like a typical figure of or typical rule of thumb is that we make the bit period sort of greater than 4 times the broadening. Okay, so you can see that from here, basically the bit rate 1 over TB is limited to 1 by 4 times the broadening, or if you put okay. So again, we had already discussed this. So for example, if you have an LED with, let's say, source bandwidth 15 nanometer at a wavelength of 1.55 micron, right? So the D here is about 17 picosecond per nanometer per kilometer, right? So from here, if you put these numbers into this formula, you get the bit rate times the length. Link length is limited to about 1 gigabit per second kilometer. Okay. So now we can do better if we go to a wavelength which is near zero dispersion. So then basically we get rid of this term, and now this beta 3 term. So okay, so we'll have this term. So now you can see the broadening goes as the third order dispersion and now proportional to the square of the bandwidth, right? Again, recall we had this discussion on if d is 0, then now the dispersion slope starts limiting me, right? So this we could also write as like the dispersion slope L times L times delta lambda square. So when this dispersion slope was yeah, so there's a question why third order dispersion. So now that's what we are discussing now, right? So again, depends on where we are operating, right? So if we take a standard single mode fiber, if we are operating at 1.55, then you can see that D is about 17 or beta 2 equivalently is about 20 minus 20 picoseconds per kilometer, right? In that case, this term dominates over beta 3. But now let's say if you move to around 1.3 micron, then beta 2 becomes very small, and then now this term becomes important. Or at the same wavelength, if you now use a dispersion shifted fiber, right? Then okay, so again, now we can get a similar expression for the bit rate times distance. Now it's limited by the dispersion slope. And again, if we take similar numbers here, and a typical value for the dispersion slope, about 0.1 picosecond per nanometer square kilometer, then this value comes out to be 20 gigabit per second. Okay, so by moving to a wavelength close to the zero dispersion, we can gain like an order of magnitude a little more in terms of bit rate or propagation distance for incoherent sources. Okay, and one can actually just sort of use linear systems theory and define like a fiber transfer function, right? So you have some input pulse here, and then you have some length here, and then you have an output pulse. So if you take input, so power versus time, the input pulse, and then the output is some function here which is broadened, right? Then we can define a fiber transfer function here, like hf of t. Right, so consider this as some linear system which transforms the input pulse into the output pulse. Okay, so this you can do for incoherent sources because basically, again, for this broad bandwidth, right, you have these different frequency components which are not sort of coherent with each other. Okay, so they sort of propagate independently, right, and because of the delay between them, you get this broadening. Right. So basically, the power is sort of carried by different frequency components, and they all get delayed, or like as we do previously. Like you can section this. You can say this part is carried by frequency component, some bandwidth omega 1, omega 2, omega 3, right? And they all travel at different speeds to arrive now at right. And so this you can just treat like so this just looks like some delay, right? So you can treat this as a linear system and define some fiber transfer function here. But you can only do this for incoherent sources, right? For coherent sources, what happens is again, so now basically you can't assume that the powers are all sort of the fraction of the powers carried by the different frequency components are independent because since now you have well-defined carrier, right? So you have well-defined phase, and you can get interference, right? So basically, the power is defined as the mod square of the amplitude, right? And because now we have here well-defined phases, and basically chirping is basically the change in phase, right? So you can see that this is no longer linear system anymore, right? So we know how to calculate this A of t on propagation, but since the power is mod of a square, like for coherent sources, basically we have to use this pulse broadening formula, and we can't define a transfer function like this. But for incoherent sources, we can. It's sometimes useful to use this kind of transfer function, because then you can just use sort of linear systems theory that we know from electrical engineering, right? And we can treat this as a linear system, and then try to have blocks, electrical blocks after we receive, to compensate for whatever distortion this linear system caused, right? By having, for example, electrical filters afterwards. So that's one way to compensate for dispersion, right? In the electrical domain, after you detect, you can have appropriate phase filters now, like to cancel out the effect of the cycle. Okay. So let's just briefly look at how we can define a transfer function for the fiber. Again, only in the case where the source is incoherent. Right, so I can define an impulse response h of t, or a frequency in terms, the fiber is acting like a filter with a spectrum h of f, right? Which is the Fourier transform of h of t. So basically, the output pulse, you can write as a convolution of the fiber impulse response and the input pulse, right? And this fiber filter function is basically the Fourier transform of this impulse response. Okay, so for this case, when the source is incoherent, we won't go through the details again, but we can define this filter function for the fiber. Okay, this is F2. So this is 1 over square root of 1 plus I f over f2, then exponential of e to the minus f over f1 square divided by 2, again 1 plus I over f over f2. Right, f1 and f2 are constants here, which depend on the beta 2 and beta 3 of the fiber. Okay, so you can see, so this looks like some Gaussian function, right, in frequency, and this looks like some Lorentzian function, right? If you take the magnitude, this looks like 1 over 1 plus f square, like a Lorentzian function, right? So both of these parts look like some low pass filter, right? So Lorentzian function, looks like this, right? And this looks like a Gaussian function, which also looks like this. So basically, you can model the fiber as some low pass filter, right? To mimic this effect of pulse broadening, right? So again, you know that a broadening in the time domain you can equivalently represent as sort of narrowing of the frequency domain. that's not what's happening, recall, right? Like the spectrum is actually not changing as we discussed. It's just that they are all getting delayed with respect to each other. But we can model the fiber like a linear system like this to mimic sort of the effect that we get. Okay. Again, so basically we've gotten rid of any phases or anything. We're only talking about powers and intensities here, right? So basically this is not the exact transfer function that the fiber is doing, right? But this is an effective transfer function that we can use to model what the fiber is doing for in case we are using incoherent sources. And it becomes easy to analyze in such a case, and also to compensate using electrical filters later on. Right, so this F1 and F2 are constants here. So F1, right, so this basically looks like a low pass filter. F1 depends on the beta 2. Right, so this broadening factor here is like beta 2L, right? So this basically sort of 1 over the broadening factor. Right, so basically you're cutting off frequencies sort of above F1, right? So that means you can see that if you have frequencies up to F1, basically the extent in time domain will be 1 over F1. That would be the broadening, right? So that's what we have here. And in case we include the beta 3 also, so F2 delta omega is square now. Okay. So okay, so depending on the fiber we're using and the wavelength we are operating, F1 and F2 can have, like, if for example, if you're operating near the zero dispersion point, then F1 is really large, right? Beta 2 is close to 0. And then F2 will be finite, depending on beta 3. Or if you're operating away from the zero dispersion point, then typically F1 will be small compared to F2. Right, so you have two frequencies here, and then the effective cutoff frequency of this low pass filter will depend on where F1 and F2 are. Right, so in the typical case where you're operating away from the zero dispersion point, F1 is smaller than F2, right? So basically this term, F1 term, will determine the filter response. In case you're operating close to zero dispersion, then F1 becomes larger than F2, and then F2, this term will determine your fiber response. Right, so in other words, so you can take the limit here, right? So if so away from zero dispersion wavelength, F1 is much smaller than F2. Right, so the frequencies which are of interest now are up to F1, right? And F over F2 we can neglect because F2 is much bigger. So this is just 1, and here also F over F2 we can neglect. So this filter response you can see just becomes a Gaussian like filter function with cutoff frequency F1. Right, so this just looks like this, like a low pass filter, right? Cutoff frequency F1. So for example, if you consider the fiber like this, then you can define a fiber bandwidth, right? It tells me like, again, what is the data rate allowed by this fiber? What is the bandwidth, channel bandwidth? And you can see that, again, it will be like F1, which is given by the beta 25. If we operate close to the zero dispersion wavelength, so now F2 will be much smaller than F1, right? F1 will be very large because beta 2 is near 0. So now, basically here, F1 is very large. So F over F1 is very small. So this is like e to the 0. So this is just 1. So you can see the fiber transfer function in this case will just be 1 over, right? So again, like if you look at the magnitude, right? So again, this looks like a low pass filter. Right. So you can calculate, for example, what is the 3 dB cutoff frequency for this, at which point this function goes down to half. So that's something proportional to F2. Okay. 10 minutes, so maybe. Okay, so that's the case for sort of when the sources are incoherent. Okay, now we can look at the other limit where the sources are coherent. Right, so this is much less than 1 in this formula here, the general formula. Yeah, so here if we take Bs much smaller than 1, basically, yeah, so that's the formula we sort of started with, right? So we neglect Bs here. So again, if you look at first the case of if you operate away from the zero dispersion wavelength, so beta 2 will be dominant. Okay, so let's also for now assume unchirped sources. coherent sources which are unchirped. So C0 is 0. Okay, so again, so first case is away from dispersion wavelength, so beta 2 dominant. So in this case, you get the pulse width at the output. Right, so here C0 we just take 0, here we neglect Vs, and this term we neglect. Okay, so we get like this. So unlike the incoherent case, you can see, so if you consider sort of the broadening like this, right? So this is the input, this is the output, this is the broadening factor. The broadening factor depends on the input pulse width itself, unlike the incoherent case. Right, so if we take this as some delta t square, you can see that the broadening induced due to dispersion is basically just beta 2 L over T naught. Right, so this is basically like L over L magnitude. Right, so the amount of broadening is basically just how many dispersion lengths you have. Another thing to note here is that actually, so the final pulse width, so for a given fiber, right, of some length L and DVD coefficient, let's say we can control what our input pulse T naught is, right? So you can see that there's a term which increases with T naught, and the second term decreases with T naught. So actually there's an optimum T naught here which will minimize TL. Right? It's not a monotonic function like for incoherent sources, right? But here you can actually minimize TL, right? So, so if you minimize TL with respect to T naught, you can find an optimum pulse width at the transmitter to minimize the pulse width at the receiver, right? And you can check that happens at T naught equal to the magnitude of beta 2 times L. Okay, and for this, the minimum pulse width that you get at the receiver is also so square root of 2 times. Right, so that's the minimum pulse width I can have at the receiver for a given fiber with length L and GVD beta. Right? And that happens when my input pulse width is of this. For any other pulse width, either higher or lower than this, this received pulse width would actually be longer. Right, so that's one interesting feature of coherent sources. So if I plot TL versus T naught, right, there's actually a minimum. Right, and again, if I say that like my bit period has to be sort of like 4 times, at least 4 times the received. So TL, remember, is like a half width, right? So we're defining Gaussian pulses here, e to the minus t square over TL square. So TL is like sort of the half width. So typically we keep the bit period like 4 times this TL. So this would mean that so TB is 1 over bit rate. So bit rate times TL has to be less than 1 by 4, and for TL again has to be the minimum value of TL is this. So if you put that in here, so we can get what the maximum bit rate is. Okay, so the maximum bitrate scales inversely with the square root of the GVD coefficient, also the square root of the length. Okay. So if I want to increase the link length by 4 times, my bandwidth goes down by half, maximum data rate possible. Right? Recall this is different from the incoherent case where this was linear, right? We had beta was less than some 1 over beta 2 L delta omega, right? So it was linear with L, but now here you can see that for coherent sources now it's square root of L. We can also see the case where now let's say we go to close to zero dispersion now. So of course we can improve things, right, by going to close to zero dispersion wavelength. So here beta 2 is 0. So we neglect this term and only now we have beta 3. So you can see then TL can be written like this. Okay. Again, so now we can define this as some broadening factor. Right. So now the broadening you can see is the beta 3 third order dispersion times length divided by square of the pulse now. Okay. So here in this case, it was beta 2 times length divided by pulse width. Now we have pulse width square in the denominator. Magnitude. Okay, so again we can use the same argument here. So again you can minimize TL with respect to T naught again, right? So this first term is increasing with T naught, the second term is decreasing with T naught. Okay. But now when you minimize, so you can see that because of, so here we have a T naught to the fourth, right? T naught square whole square. So here we had a T naught square and then also T naught square here. Here we have T naught square and T naught to the fourth here. So when you actually minimize, you see that the minimum pulse width at the receiver will scale with beta 3 times length cube root. So here it was square root, right? Here it will be cube root. Okay, and by the same argument like this we had here, so the maximum bit rate will be cube root of, will scale inversely with cube root of length, not square root of length, right? So you can see this is even better, right? So here I can increase the length even more without compromising too much on the data. Yeah, so we're exceeded time, but maybe just I'll quickly wrap up this topic with a couple of graphs here, just to sort of summarize all this. So we can see already. So for coherent sources, the data rate scaled inversely with the link length, right? And so the worst case you can imagine is like if you're operating with incoherent sources away from the zero dispersion, where beta 2 is dominant. The first improvement you can do is stay with incoherent sources, but go to zero dispersion. Then now you're limited by third order dispersion. The next improvement you can actually do is go to coherent sources, right? And then coherent sources, if you're away from zero dispersion, then now your bandwidth scales inversely with the square root of the length. And now if you, with coherent sources, if you go to zero dispersion, then you get sort of the best case scenario where the bandwidth now scales only with the cube root, or inversely with the cube root of the length. right? So for the same link length, the maximum data rate that you will have will be for this case. When you're operating with coherent sources at the zero dispersion wavelength, right? The next best would be coherent sources but away from zero dispersion. Next best would be incoherent sources at zero dispersion, and the worst would be the lowest data rate that you will get for a particular link length would be for incoherent sources and also away from zero dispersion. So if we sort of summarize all this, and let's say I'm plotting the maximum data rate possible, right? So this is in gigabit per second as a function of fiber length. Okay, so length here in kilometers on the x-axis, data rate in gigabit per second on the y-axis. So the worst case scenario is when I have an incoherent source. Okay, I can operate at very low data rates for sort of very small distances. Okay, so this is for let's say a laser diode with 5 nanometer bandwidth. Okay, and the dispersion coefficient is about 16 picosecond per nanometer per kilometer. Basically, again, so if you take 1550 nanometer wavelength for a conventional single mode fiber, this is sort of the dispersion value, right? So you can see that this is very bad. Right? I can go for maybe like 10 kilometers at less than a gigabit per second. I can improve things by narrowing the source bandwidth. So okay, so if I go to 1 nanometer, right? So sort of I improve by 5 times. Okay, and this variation here of B versus L, right? So in both these cases, so here B is inversely proportional to L, right? Linearly with L. Okay, so if I go to coherent sources, then things improve a lot. So the curve now looks like that. Okay, so the slope is halved. So this is on log scale, right? So from 1 by L, I go to 1 by square root of L. So the slope is sort of halved on this log scale. So this is for coherent source, so source bandwidth negligible compared to the data rate. Okay, and all these three are for the same dispersion line. Okay, so this. Okay, so if you're operating away from zero dispersion, right, with some finite dispersion coefficient, right, the worst is a broad incoherent source. I can improve things by narrowing the source bandwidth and ultimately going to a coherent source, right? And in this case now, the data rate is scaling as square root of it, right? So this is going down slower, so I can go for longer lengths for the same data rate. And the best I can do is now if I go to zero dispersion wavelength with incoherent source, with coherent source, sorry. So then this slope is now even smaller, right? So this is now cube root of length. So the coherent source, right? So these two are coherent source, and these two are incoherent source. Okay, so yeah, we can do basically orders of magnitude better now. So if right, so modern day systems, if we use coherent sources single frequency lasers and we compensate for the GVD, right, either by operating at a zero dispersion wavelength or by compensating for the dispersion by having, we'll discuss maybe some dispersion compensation techniques in the next class. Right, so basically we compensated for the second order dispersion, then we are only limited by the third order dispersion. You can see that we can get like hundreds of gigabit per second over hundreds or thousands of kilometers. Okay, and finally just this importance of the chirp, right? So if we can also do a plot with chirp. So if we plot this figure of merit bit rate times length, so gigabit per second kilometer. Again, this when we are talking about chirp, it automatically means it's a coherent source. So this is the chirp at the transmitter, the input chirp C0. So let's take again this beta 2 value to be sort of minus 20 picoseconds per kilometer. So this is the typical value at 1.55 micron for the standard single mode fiber. Right, so as we vary the chirp, right, so now you can see beta 2 is negative. That means the optimum will happen when the chirp is positive, right? Remember, we want beta 2 times C to be negative. That's when we first sort of get compression up to some point and then it starts broadening, right? So that's the best case scenario. Okay, so this thing peaks sort of somewhere like here for C not equal to plus 2. Okay, so it's better than C not equal to 0. Okay, so if you have a fiber with opposite dispersion plus, then this curve will flip about 0, right? Then C naught of minus 2 will probably be optimum. So, right, and so just to be aware that so typical semiconductor lasers which are used, if you just directly current modulate them, then they actually end up having a negative chirp. Okay, so you can see that's actually very bad for a standard fiber. If you use a standard fiber link with this dispersion value at 1.55 micron, then if we just directly current modulate the laser, the C naught value is somewhere here, like -5 or something. You can see that's far from the optimum. Okay, so either we compensate for dispersion to make it net positive, or we use some other form of modulation, not current modulation, to chirp it positive. Okay. Anyway, so I've exceeded time by about 10 minutes, so sorry about that, but just wanted to finish this discussion. Any questions? Ayushi has raised her hand. You can.
Yes, sir. I have a basic question. Sir, you mentioned the delta lambda for laser and LED in nanometers or maybe in picometers. So what is that delta lambda is called as? Is it spectral width or line width?
Yeah, I mean, both terms are used. So you will see sometimes line width quoted in like nanometer. You will sometimes see line width quoted in megahertz or gigahertz.
Yes, sir.
You will also see spectral width quoted in. So yeah, these terms are all interchangeable. But yeah.
So, is delta lambda and delta f, change in frequency and change in wavelength are both the same things or different things? And in what case they are different?
I mean, it's just it's this defining the same thing in different units, right? As we discussed already. So yeah, so f c over lambda, right? So delta f, the bandwidth and frequency, is c over lambda squared delta lambda. Right? So this is a fundamental quantity, right? Delta f in hertz. So it does not depend on the center frequency or the center wavelength, right? Whereas this delta lambda, you can see, depends on the center wavelength, right? So, for example, 100 gigahertz bandwidth at 1.5 micron is not in wavelength units is not the same as 100 gigahertz at 1 micron, right? Delta lambda will be different for both these cases.
And sir, one more question. So, sir, is link length is all the optics including the transmitter and receiver part? So, what is exactly link length?
It's just the fiber length, right? Because that's the length. Because I mean, transmitter is like just a chip, right? It's a laser with fiber attached, and receiver is also just a photo detector on a chip. So
optical link and link length both are the same thing, sir.
Yes, yeah. So link length is basically just the fiber length, effective fiber length. Yeah.
Okay, sir. Thank you so much, sir.
Any other questions?
Sir, is spectral width and bandwidth are both the same thing? I'm still confused.
Yeah. Yeah. This is sort of the same thing. Yeah. Yeah. I mean, bandwidth is sort of used across different disciplines of electrical engineering. Line width is more used for optical, like optical things, right? Spectral width, sort of, yeah, it's a general term that. But yeah, all of them ultimately, fundamentally mean the same thing.
Okay, thank you, sir.
Yeah. Okay. We can stop here and then meet on Monday. Have a good weekend, everyone. Take care. Bye. Sorry, so one more question. Is it possible to compensate for third order dispersion also? Yes. In the same way that we compensate for second order dispersion, we can also compensate for third order dispersion. So recall what is happening in dispersion, right? So when we're discussing this equation, basically dispersion is just adding a phase in the frequency domain, right? So beta 2 times L times omega square. So the beta 2 adds a quadratic phase in frequency. Beta 3 will add a cubic phase in frequency, right? So if you can compensate for that, then you can compensate for that order of dispersion, right? Equivalently, again, recall what is happening, right? Since this phase, so these phase factors are going as beta 2 times L, beta 3 times L, right? So imagine you have some particular length of fiber with some beta 2 and beta 3, right? So that will give me some beta 2 effect which is beta 2 times L, and then some third order effect, which is beta 3 times L. Now, if I could have another fiber after that with the opposite signs of beta 2 and beta 3, right? So then the phase that it will be e to the minus, right? Beta 2, if it's the opposite sign, the phase will be of beta 3 also, right? So if you can somehow, so if the first fiber is length L1, second fiber is length L2, if you can somehow like have beta 2 for the first fiber times L1 to be negative of the beta 2 times L2 of the second fiber. Similarly for beta 3, if you can do that, then you can compensate for beta 3, right? So, but yeah, maybe so in the beginning of the next class we'll discuss some dispersion compensating techniques. But yeah, in principle you can compensate for beta 3 also, but it's a little bit more difficult. But typically, performance limited by beta 3 is still, as you can see, like hundreds of gigabit per second over 1,000 kilometers, right? That's still, we haven't utilized all that capacity. Okay, so typically for most practical cases, we don't compensate for beta 3, right? Once we exceed this limit, right, then we can worry about compensating for beta 3. But even just limited by beta 3, there is so much bandwidth and over such a long distance available that even if you just utilize this, that's quite. Remember, this is for a particular wavelength channel, right? Just one wavelength.